Today we will go about with a basic introduction to probability. It's going to involve understanding sets, experiments, and probability. We begin by defining what an experiment is. It is a repeatable task, and the task has a well defined outcome. Examples of experiments would be a coin toss, drawing a ball from a bag containing balls, or choosing a student from this class, or maybe even uh, choosing three students from this class. Now, remember, in this last case, we might need to specify how we are choosing students from this class, which might be with or without replacement. So, we will talk about this later in the video. There is a set attached to every experiment. We call it the sample space, and it is the set of all possible outcomes of the experiment. This set is usually denoted by the symbol script S. Some examples would be in the case of a coin toss, the sample space would be heads or tails. For the ball draw experiment, the sample space would be the set of all balls in this bag. When choosing a student from this class, the sample space will be all students in this class. And if you're choosing three students from this class, the sample space is going to be all groups of three students in this class. There are some considerations to keep in mind in the latter case. For example, does order matter? An event is a collection of possible outcomes of an experiment. It is going to be a subset of the sample space script S. Some examples of events would be in the case of the coin toss, getting a heads would be an event, or when choosing a student, uh, uh, choosing the student named Sarah could be an event, right? So the selected student is Sarah. To make precise statements, we would need some understanding of basic set theory. So let A and B be two sets. We will say that a set A is a subset of B if an element X belonging to A implies that X belongs to B. There is a typo in the video. It should have been X belonging to B. We say that A equals B if A is a subset of B and B a subset of A. In the first case, the relationship is of containment, and in the second case, the relationship is of equality. We now talk about operations with sets. The first operation is the ability to take a union. A union B is going to be the set of all elements that are inside A or B. A intersection B is going to be the set of all elements X that are in A and in B. This is denoted by A intersect B. Finally, the complement of A is going to be the set of all elements that are not in A. And the symbol phi is going to denote the empty set, that is the set that contains no elements. So let gamma now be an indexing set. So gamma can either be a finite set or it can be an infinite set. In the case of infinite sets, it can either be countable or uncountable. In either of these scenarios, we can fix the sample space and let A alpha, for alpha inside gamma, be a collection of subsets of script S. Then the union over gamma of all the A alphas is going to be the set of all x's such that x lies inside A alpha for some choice of alpha inside gamma. Similarly, the intersection along gamma is going to be the set of all x's inside the sample space such that x lies inside A alpha for every alpha inside gamma. We say that A and B are disjoint if the intersection of A and B is the empty set. A and B would also be called mutually exclusive in this case. A1, A2, A3, and so on would be called pairwise disjoint if the intersection of AI and AJ is empty for any pairs of IJ such that I not equal to J. Also, A1, A2, A3 will be said to be a partition of S if A1, A2, A3 are all pairwise disjoint, and if the union is the entire sample space S. Finally, the set of all objects of interest would be called the universal set. This is typically the sample space of an experiment that we are concerned with. With all of this background set, we can now talk about axioms of probability. Let S be the sample space of an experiment, and let A be an event, that is, A is a subset of S. What we want to calculate the chance or the probability that A occurs. So we would denote this number by the symbol P of A, or we call it the probability of A. Note that P is a function whose domain is the set of all events corresponding to a sample space that corresponds to an experiment. We now specify the axioms for the probability function P. So the probability function P will have to satisfy three axioms. The first axiom is that P of A has to be greater than or equal to 0 for any event that is any subset of the sample space S. The second axiom tells us that the probability of the entire sample space is 1. And the third axiom relates to a collection of subsets of S, which are pairwise disjoint. It tells us that the probability of the union of these subsets is going to be the sum of the probabilities of each of the events. Using the axioms of the probability function, we could derive some properties of such a function. The first property is that the probability of the empty set or the probability of not having an outcome is going to be 0. Given an event A, the complement of A is going to correspond to the set of all outcomes that are not in A. Note that the intersection of A and A complement is the empty set, and the union of A complement and A is the entire sample space S. So using the third axiom, we must have that the probability of A plus the probability of A complement is probability of S, which is 1, using axiom 1. And as a result, we have that the probability of A complement is going to be 1 minus the probability of A. We get into a little bit more of set theory. Given two sets A and B, A minus B is the set of all elements that lie inside A but not in B. The set A is going to be the disjoint union of A minus B and A intersect B. And as a result, the probability of A is going to be the probability of A minus B plus the probability of A intersect B, which lets us conclude that the probability of A minus B has to be probability of A minus probability of A intersect B. Now we note that the set A union B can be decomposed into A minus B, A intersect B, and B minus A. All of these are pairwise disjoint sets. And using the third axiom for probability, we have that the probability of A union B equals P of A minus B plus P of A intersect B plus P of B minus A. We follow through with this calculation, to arrive at the formula for the probability of A union B, which equals P of A plus P of B minus P of A intersect B. We wrap up this video with some pictorial description using Venn diagrams. So Venn diagram is going to have the universal set as the rectangle and the sets A and B as the elliptical blobs. The set A union B is denoted by the set of all elements inside A or B, which is the shaded red region. And the set A intersect B is the set of all elements that are inside A and B, which again is going to be the shaded red region. We also draw Venn diagrams for A minus B. The red region corresponds to the elements inside A minus B. The blue region is the a set of elements inside A intersect B. Similarly, B minus A has been pictured. And finally, a description of the entire sample space using A union B complement, A minus B, A intersect B, and B minus A. This is all for now. Take care and see you around.